Thank you. Okay. Wait, I will minimize just the window so it doesn't. Okay, it's not in the middle. Okay, so transfer operator approach is a powerful tool for to study one-dimensional and quasi one-dimensional systems. So what I will do here, I will start by giving you an introduction on classical transfer operator in statistical mechanics, and then I will try to explain you a couple of examples where you have a supersymmetric extension of this transfer operator. Of course, for people who already know transfer operator, the first part may be boring, but for people who don't know, it's a very nice tool to discover. Okay, so let's start with part one. So I will take a very precise example. So as example, I take a spin model in dimension one. So example, spin model in d equal 1. Okay, so let's fix the setting. We have a volume in dimension 1, and I will take as a volume a subset of ZD. So this is minus L, L intersection with Z. So we have here points between minus L and L. We define now this volume as spin configuration, phi, which is a map between lambda L and here I take real valued spins. So for each x, I assign a spin at the point x, which is just a real variable. And this is my spin configuration. And third, I define for each spin configuration an energy, which has a special form. I take first a sum of gradient square. And since I'm in dimension 1, I can write explicitly the sum. I sum over all the pairs. So I sum between minus L and L minus 1, phi x plus 1 minus phi of x square. I put some parameter in front, and maybe I divide by 2. This is not so important. So plus, and then we have a potential term. So again, I sum between minus L and L. And in each point, I have a potential depending on the spin in that point. So here we have the potential energy, and the typical example is d of phi is phi square. So, okay, just the parabola. Or you can always think that we are looking at the perturbation of phi square. And this part is the kinetic part. And the parameter J is strictly positive. And this means that we have ferromagnetic interaction. Okay, so now this depends on the finite volume. Now we can define a finite volume Gibbs measure, which is given depending on the volume, and is given by the weight exponential minus h phi, product over all the x in my volume, d phi x. Here we have the bag mass, a measure, and we divide by a normalization. Where, okay, z, I write it here, z is the normalization, it's just the integral of e exponential minus h times the product of d phi. And here we are integrating over lambda L, r to the lambda L. Okay, so this is the standard, this is a standard construction in equilibrium statistical mechanics. And what is the goal now? Well, we want to study the thermodynamic limit of this measure. So the goal is to study the thermodynamic limit of d mu L. So we want to study the limit L going to infinity. Okay, but now here, to give you an example of how the transfer operator method works, I will concentrate on two precise informations on this measure, the average and the covariance. So here we consider the average, the x0, and the covariance at point x1 and x2. And we ask what happens when L goes to infinity. Okay, so this is what we want to study. And now how that, so we have to do with an integral over 2L plus 1 variables, with L going to infinity. So the idea of the transfer operator is to map this problem to a dual representation. And so here is the dual representation. I will manage maybe dual representation. Okay, so we take our, I will now do this explicitly in the simplest possible case. I will take the average in a particular point. So remember, this is the integral of the product d phi j e minus h phi. And here we have our observable, and we have to divide by the normalization. H phi. And now the point is that we can now rewrite the numerator and the denominator in another way. And so how do we do? So we take, so here I still my fraction. So above, I have a certain operator t to the power L plus x0 applied to a function f, which I call f on the left. Then my observable, the same operator to the power L minus x0 applied to a function which I call R. And now what you have to think is that I have a function here on the left, a function on the right, and the operator t starts here, maps to something this point, and then goes in this direction. Here we go backward until we get in the middle, and in the middle we have also our observable. Okay, and below, well, I can do exactly the same for the partition function, except there is no observable in the middle, but I can still integrate step by step until I get to the center. So I have exactly the same expression, f left, t, L minus x0, f right. Okay, and oh, I lost page. New page attend. Yeah, hopefully. Okay, I forgot to create enough pages. Okay, so now let's write explicitly what is this operator t. So I will write it here. So t is an operator with integral kernel. So if I apply t to a function and I compute it in phi, phi is a real variable. This is the integral over d phi prime on R, a kernel k phi, phi prime f of phi prime. And now what is this kernel? Phi, phi prime. So in the case we are considering, we take exponential minus v in phi divided by 2, exponential 1/2 phi minus phi prime square, and I have a j here, e minus v phi prime divided by 2. Okay, and the point is that we can organize our integral starting from the last variable. We integrate one variable at a time, and the corresponding integral is described by this operator with an integral kernel. And now the last, so here I also wrote a function f left and f right. So I have to give that. Fl left and f right, in this case, is just exponential minus v phi divided by 2. So if you are wondering, here I'm just taking 3 boundary conditions. I didn't put any special boundary conditions. Okay, what remains? Ah, yeah, and the observable, and now O of F, well, this is just a multiplication operator, which is multiplying the function by phi. And it describes this term above. Okay, yeah, and finally, what are these parentheses? Well, this is just a scalar product in L2. So Fg, this is the integral on R, I try to remain consistent with the notation, F phi G of phi d phi. Okay, this is a well-known operator. An operator with this form is generally called a CAC operator. So T is a CAC operator. Actually, in particular, if the potential is just phi square, well, in that case, you talk about harmonic CAC operator.
Since we have Polish people in the audience, perhaps they should be called CATS operators.
Oh, with an S? Z? How?
It's pronounced CATS, I believe, but never mind, continue. Sorry.
Okay, I'm sorry. Okay, I may be writing this wrongly. I'm copying from the notation is from the book of Helfer.
It is spelled correctly. It's KIC. That's correct.
Ah, CACS. Well,
CATS.
CATS. Okay, you have to. I have to try. So you have to tell me several times. Okay, so let's compare a bit what we gained. So if you look here we have 2L plus 1 variables, L going to infinity. And now here, well, here we have an operator acting on R, on a function of R, so we have one of 2 variables. And the point is that this capital L, the volume, is now just a parameter. So now what we have to study, we replace an integral on many variables with an operator with very high powers of an operator. Okay, which may be good because then this operator may be complicated, but still it's an operator on 1, 2 variables, so we should be able to study this operator. Okay, so wait, maybe I take this away. Okay. Okay, so we go from 2L plus 1 variables to an operator T to the power L. Okay, and T typically maybe, okay, T typically some operator, for example, from L to R to L to R, or something like that. So we have one variable, which is nice. Okay, now of course, this helps only if you can indeed say something about this operator. Okay, so let's look at this operator. So now we want to study the operator T. Okay, and now I don't want to be very precise, but assume that the potential V is nice enough. Assume V is nice. So, for example, smooth, and let's say that V goes to infinity fast enough when phi goes to infinity. Okay, then T is indeed an operator from L2 to L2. And it has a number of properties. It's self-adjoint. It's compact. Actually, it's Hilbert-Smith. Compact. And, well, if you look at our kernel, which was here, so here is our kernel. Now, it's a product of exponentials. Oh, well. So it's strictly positive for every phi and phi prime. So we know that in addition, k phi prime is strictly positive everywhere. Okay, and actually this tells us we know a lot about this operator. So this means that, well, the spectrum is real, it's compact, so the spectrum outside zero is point spectrum. So sigma t minus 0 is just point spectrum. What else do we know? Yes, if we take the norm of the operator, this is an eigenvalue, and it is a simple eigenvalue. And for this eigenvalue, we can find an eigenvector which is strictly positive. So we can find a V0 in 2, which is solution of the eigenvalue equation. And in particular, V0 is strictly positive, almost everywhere. We also know something more. We know that if we take any other eigenvalue, so for any other element in the point spectrum, well then lambda, which is not lambda 0, then in norm, lambda is strictly smaller than lambda 0. So minus lambda 0 is not an eigenvalue. And the corresponding eigenvector cannot be strictly positive or strictly negative. So it must be, if it is positive somewhere and negative or 0 somewhere else. And last but not least, now we can, since T is compact and has all these properties, we can write T in the following way. T is lambda 0 times P0 plus T1, where P0 is the orthogonal projection on V0, the eigenvalue corresponding to the largest, the eigenvector corresponding to the largest eigenvalue, and T1, where T1 is the operator restricted on the orthogonal complement. So what happens is that T1 P0 commutes with T1 that's 0, and T1 can be written as a sum of projection on the eigenvectors corresponding to all other eigenvalues, but they are smaller. So the norm of T1 is strictly smaller than 1. So we have a spectral gap. And I think I wrote everything. So all these properties, they go under the name of Krein-Ruthman theorem. Or if you're talking about matrices, this is the simply Perron-Frobenius. Okay, and this is a simple version of Krein-Ruthman. There are more general versions of this theorem. Okay, so now in our case, our operator is self-adjoint, it's compact, so we can apply this theorem. So let's see what we learn. So application. So let's take our t, and we take now t to the power L. So we take the representation here. When we take t to the power L, well, then we get exactly this form. We have lambda 0 to the power L. P0 is a projection, so P0 to any power is P0. P0 commutes with T1, so there is no mixed term. So the only thing that survives is T1 to the power L. And the norm of T1 to the power L converges to 0 when L goes to infinity. Okay, so now we can take this representation and insert it into our expression, which was somewhere here, which I will maybe try to copy. And use this to compute our average. Okay, so I'm here. Okay, so yeah, paste. Okay, so okay, here is our average of phi 0. Now we replace our representation. We get a lambda 0 from above to the power 2L. There is a lambda 0 below to the power 2L, so that disappears. And then we have here P0 plus T1 to the power L plus X0 applied to our F left, the observable P0 plus T1 to the power L minus X0 applied to F right, and it was too short, okay, and below, well, we have the same L plus X0 applied to F left, and then the same here without the observable F right. Okay, and now you see that this term, the term here and so on, they will converge to 0 when L goes to infinity. So all these will converge and this disappears. So when L goes to infinity, we get P0. Actually, I can write it in a simpler way. F left, P0 observable, P0 F right, divided by F left, P0 F right. Okay, but now P0 is the projection, the orthogonal projection on D0. So now I can write this explicitly as FL, scalar product with V0, V0, O V0, V0, F right, and I divide by FL V0 times V0 F right. Now, you may be scared that we are dividing maybe by 0, because we are dividing by something, we don't know if this something is maybe 0. So note, what do we know? We know that FL was an exponential. So this is something strictly positive. And we know that this is part of the assumptions, the results of the theorem, that the vector V0 is strictly positive for almost all phi. So the result is that the scalar product F0, V0 FR, this is the same as, this is strictly positive. And the same for the other. So we are not dividing by 0. Okay, and now we can simplify all that, and then the result is a nice simple formula, is the integral on R of V0 of phi square phi d phi. So if now we know we have a way to find an approximate expression or find exactly V0, well, then we have found the limit of the average. Okay, we can do exactly the same kind of page. We can do the same kind of arguments to show that, similarly, we can show, for example, that the log of the partition function converges to the log of lambda 0 when L goes to infinity. And we can show that the covariance x1, x2 converges when L goes to infinity to, so we write here the final expression, V0, O, T1 remains in the middle, x2 minus x1, O, V0, where O is some observable. And now if I put absolute values, this is bounded or equal by the norm of the observable times V0 square times the norm of T1 to the power x2 minus x1. And now, since this number is strictly smaller than 1, we get immediately that the covariance decays exponentially. With the distance between the 2 points. When we want now, if you want to know something more precise, for example, what is the rate of this exponential decay? Well, then we know we need something more, but we don't need so many information about our operator. So what do we need? We need to know, well, for these functions I showed you, we need to know lambda 0. We need to know the vector v0, and we need to know the norm of T1, which is actually the absolute value, the size of the next eigenvalue, so the spectral gap. That's all the information we need. Okay. Now, of course, at this point, we should study really our operator to see if we can extract this information. There is no standard method to do that. So if we are in the harmonic case, well, then we can do all the computations exactly. Actually, we can find all eigenvalues and eigenvectors exactly. In the general case, well, it depends on the situation. Generally, what we do is we play with some small parameter and approximate our operator with the corresponding harmonic operator. Or we can do in a more refined way a WKB construction. So we can either approximate with harmonic operator or a WKB construction. Or there are other things you can do. So just before I go to the second part, so there is a nice there is a nice explanation about this. This method of transfer operator, for example, is well explained in the book by Helfer. I will write this wrongly. And it is Witten Laplacian and semi-classical analysis. But there are others, of course. Oops. Analysis. Okay, so this is all I wanted to say about the classical case. Okay, now I would like to show you a little bit what happens so that you have some, you can construct generalization of this operator in a different context, but still the ideas are more or less the same. Okay, so the path 2 is when I write SUSY, I mean supersymmetric transfer operator. Okay, I will show you 2 precise examples. So my first example, example 1, is we consider the random Schrödinger operator. So now we moved in a totally different context. Now we are in quantum mechanics. And so now we consider a random matrix. Random matrix. Oops, matrix. Okay, and this matrix is defined in the following way. H is in a fixed volume minus Laplacian plus V. So this is a real symmetric matrix on this, defined on this one-dimensional interval, where Laplacian is the lattice Laplacian. And D is a diagonal matrix. D is a diagonal matrix, V minus L DL, where the elements of the diagonal are independent, identically distributed random variables. Are I, D, random variables. And I'm not now very specific about what kind of distribution we take. So here, so the motivation is to study quantum diffusion in disordered conductors. But okay, whatever the application is, so what is the mathematical problem here, where we want to study the limit of infinite volume of the average of the resolvent, to take a simple example. So I'm taking Z minus H inverse, and I'm computing this at the same point, x0, x0. And here Z is E plus I epsilon, where E is a real number, and epsilon is positive, and normally epsilon is very, very small. Okay, now H is a real symmetric matrix, so it's diagonalizable. All the eigenvalues are real. So if we take Z to be complex, this matrix is invertible. So all this is perfectly well defined. Now the question is to study the limit when the volume goes to infinity. And I claim that the transfer operator approach can help us study this limit. Now, of course, if I look at these, I don't see anything similar to a spin model where we could reorganize this as a high power of a certain operator. So the first step is to first map this problem to something that looks like a spin model. Okay, so this is our first task. So the first thing is I want to map to a spin model as in the first part of the talk. And I will put spin more or less because it will not be a standard spin model. Okay, this is done using the supersymmetric representation. And I will give the result. So the average of this matrix element in x0. X0 can be written as the integral of the product of x between minus L and L d phi x E minus H. Okay, I'm trying to use exactly the same notation we used in the spin model. So we have something like I gives weight, and at the end we have an observable key x0, key bar x0. And maybe here I will put below what we had before. Before we had a product over x, d phi x, and here we had h of phi, and here we had phi of x0. So it looks very similar. Now I have to define what I mean by this notation capital phi and what are these strange variable key. Page attend. Okay, so now what is phi? So remember, before each phi, the spin was a real variable. Now the spin is a vector with two real and two Grassmann components. So phi is a vector is in R2, and key and key bar are Grassmann variables. Okay, so if you know Grassmann variables, then you will have no problem. If you don't know them, well, don't worry. They are you can. These are so you can think of them as anti-commuting objects, and they are algebraic tools that help doing the computation. But at the very end, when we do estimates, they will disappear. The problem will be to, at the end, to reduce the problem to ordinary variables. Okay, so this is a vector, so we need to define a scalar product, phi prime. So this is defined the following way. This is the usual Euclidean scalar product between two vectors, and then for the Grassmann variables, we take chi bar chi prime plus chi bar prime chi, everything divided by 2. And in particular, phi square, this is phi scalar phi, that's phi square plus chi bar t. Okay, so now let's see. So now we know that our spin, instead of being a real variable, is a vector with 4 components. And now I have to define what I mean by energy for this. So the energy has exactly the same form we had above. Let me write it here, h of phi. So this is, well, almost the same form. There is a minus I over 2. So this is complex. And here we have the sum between minus L and L minus 1, oops, and L minus 1 of phi x plus 1 minus phi of x square plus sum over x d of, and here I write this phi of x square. Now remember that before here we had phi of x plus 1 minus phi of x, but we have no I, there was a j which was positive. And so now we have this problem that here we have, oh, this is not very visible. This should be better. These, yeah, no, these, so here we have oscillations or complex. Okay, so this is not going to be really a probabilistic model, but we still think of this as a spin model, as some kind of statistical mechanical model. I forgot, I didn't tell you what now is the potential. Okay, so now I still have to write what is V. So I wrote explicitly V is a function of phi square. So I can think of phi square as some variable t. So V of t is minus I z times t minus log nu hat t, where nu hat t, this is the Fourier transform of the probability distribution. So it's the average of exponential it v. So this is the only point where the fact that the potential v is random enters. Okay, so at least formally I have something that looks like a Gibbs measure. So we can say that we have a, now we write Gibbs measure, which is of course not a probability measure. And this will be exponential minus h phi d phi. And so even if it's not a probability measure, it looks very much like the example before. So we can try to do a representation using transfer operator. And indeed, we can do that, at least formally at the beginning. So we take, so I mean, no, this, all I'm writing is perfectly rigorous. Just so we have a dual representation. And so what do? We take our average of z minus h inverse x0, x0. So remember that this was the integral product of the phi x E minus H phi T x0. And now you may wonder why I'm not dividing by a normalization constant. The point is that the normalization is Z is 1 by symmetry. So this is not a probability measure, but it has exactly the right property. It is normalized to 1. Okay, so since I don't have a denominator, I only have to rewrite this numerator as a transfer operator, and I can do it. So what we get is, now I use calligraphic T instead of capital T to remember that now we have Grassmann and real variables. A function on the left, an observable T to the L minus x0, capital F R. And now T in F, though this is an operator with integral kernel, and it's defined in the following way. So we have integral on C prime, a certain kernel, C prime, F of C prime, and the kernel C prime is, okay, nothing is real as it's not going to be self-adjoint, so I don't need to, I don't need to symmetrize. It's easier to write it in this way. E minus I over 2 phi minus phi prime square. So this is our operator. And then the rest is almost the same as before. The observable is, well, almost. Since I did not symmetrize, then I pay a price. Here I have to multiply by V. And otherwise it's K bar, the function, and my function F left and F right, they are just 1. They are constant. And finally, what is the scalar product? This parenthesis FG is the equivalent of the L2 scalar product. So it's the integral d phi F of phi G of phi. So I did not explain what is this d phi, but this is the integral on R2, and then we have an integral on the Grassmann variables, which I didn't define, but it's possible. You can define the operation. Okay, so one positive thing is, well, we just have to study the numerator. There is no denominator. So this is what we have to study now. But then on the other hand, it looks pretty horrible because now we have Grassmann variable, and this expression is complex. It's not clear if you have a self-adjoint operator. It's not clear on which space our operator is acting. Okay, but the point is now we can take this and map it to a standard operator, an ordinary function. Okay, so I write here. So we want to map T to a classical operator, a transfer operator. Okay, so that means that there are no Grassmann variables any longer at the end. Okay, and what is the idea? Well, the idea is that if you look at, so here in our K, the potential is a function of phi square, and here we have phi minus phi prime square. So if these were ordinary variables, this would tell you that these two expressions are rotation invariant. And actually the same is true here, but we have to define super rotations that rotate also the Grassmann variables. So we consider a super rotation. So this is a linear map which lists the scalar product invariance. So phi r phi scalar r phi prime is equal to phi prime. Okay, and now comes the following result. If my function is invariant under superrotations, well, then I can represent my function as an ordinary function. So first, there exists a function little f, which is defined on R plus with complex values, such that capital F of phi square, this is little f, of phi, this is little f computed in phi square. And actually, if I really write this explicitly, this is f in phi square plus chi bar chi, the derivative of f computed in phi square. So the function f must be at least differentiable. And second, we can take our transfer operator, calligraphic t, applied to phi, and we can write this as an ordinary transfer operator applied to the function little f. And only at the end, we replace the argument of this function by phi square. Okay, now T is a classical transfer operator. And it acts, we can write, I can give you an idea how it looks like. It acts on the functions that are only of positive variables. So I can compute TF computed in R square. This is equal to E minus V computed in R square times a certain operator applied to F computed in R square. And how does this D look like? So D is the following: is exponential minus I R square over 2 times delta 0 plus R. Delta 0 is just taking the value of the function 0, and the operator R in R square, this is equal to little r, the integral between 0 and infinity, ds, e minus I s square over 2. I have here a Bessel function computed in R times S times f of s square. Okay, and here it's this is the Bessel function. Okay, so, well, it's a standard operator, but it's not as easy as the operator we have seen in the first example. There are two problems where there is this delta 0. So if I want to define my operator as acting on some LP space, I have a problem because the function may not be defined in that particular point. And second, it's complex. So no hope to apply anything like Perron-Frobenius. So we have to do things by hand. And actually, another difficulty here, we have to play a lot with oscillations. Okay, but still, one can do it. So, okay, so the problems, maybe, so the problems, to be fair, so D and R are complex, and no Klein, Rootman, or something similar. F in 0 is not defined, it's not a well-defined operator on L2 or LP. But now there is a good news. If the function in 0 is 0, well then this term disappears. We only have R, and R is a well-defined operator. So what we get is then T to the power L applied to F. This is exponential minus VR to the power L applied to F. And now the point is that now I do this morally, you can show, you have to work a little bit, that the norm of this operator is strictly smaller than 1. So you can still, even if you cannot say directly, well, I have a Peron Frobenius or something like that, well, you can still show that T to the power L converges to some projection. But you have to work a bit more explicitly. Okay, and now quickly, so maybe I should put some literature. So this was worked out in detail, and actually more things were proved, and also a more general version of this was proved. So one paper is, well, it's not recent, actually it was Campanino, and Klein in CNP, and I think it was in 86. Okay, so now let's go quickly in the last end. So a more recent example. So always a supersymmetric approach. So a SUSY transfer operator, and we take the second example. And now the second example is still something motivated by quantum diffusion in disordered materials. It's a random matrix, and this time we take the so-called random band matrix. Band matrix. Okay, how is this defined? So this is a complex valued matrix in this one-dimensional interval. It's self-adjoint. And the matrix elements, apart the self-adjointness, they are independent random variables, normally distributed. So H, X, Y is normally distributed with average 0, and a covariance which is not the same everywhere. It depends on which matrix element we are looking at. And the covariance is defined as JXY. This is one possibility. We take minus W square lattice Laplacian plus identity inverse between X and Y. And now the result is that this is something that is approximately decaying exponentially with the distance between X and Y. So if I do a drawing, the matrix is approximately, so we have a band of width W around the diagonal. The matrix is approximately 0. So the matrix elements are approximately 0 here, and they're approximately IID inside the band. This is a bit the picture. So, and the goal, again, we concentrate on this example, we consider the average of the resolvent. X0, L, and we study the limit L going to infinity. Okay, so at this point, you know what is the procedure. First, we have to map this problem to a spin model. So we want to map to a spin-like model. And this time, the spin model we obtain is slightly different. The spins, they are not vectors, they are actually small matrices. So I will write here the average of Z minus H inverse X0, X0. This is the integral. I have a product X between minus L and L. Now this time my spin is a small matrix at X. I have again an energy for the matrix, the spin configuration. Okay, now I have to explain what is AX0. Okay, so now here, the spin is now a 2 by 2 matrix with two real, actually A and B are real, rho bar and rho are Grassmann. And rho bar are Grassmann. And this is our spin. The energy of the spin configuration looks again like a kinetic term plus a potential term. So I have a sum between minus L and L minus 1. Now, okay, here I don't have a scalar product. When you have matrices, you normally take the square of the matrix and the trace. In the case of when you have Grassmann and real elements, the trace is replaced by the super trace, but it's just the analog of the trace. So here we have super trace of mx plus 1 minus mx square. And now in front, there is no I, so this is nice. This is more similar to the initial problem. So remember that in the initial problem, we had a j divided by 2, and here we had phi x plus 1 minus phi x squared. So this is more similar to our to the example, to the classical example. And now here we have a sum over x dn of x, where this potential d of m is defined the following way. It's the super trace, I'm sure I forgot something, m square, no, it should be correct, plus the log of the determinant. Now I write super determinant because it's a super matrix, minus m. Okay, so, okay, we have this strange, but still, we still have a kinetic term here and a potential term here. Actually, it turns out it's better to do, before doing other computations, we need to do a translation. We translate the matrix by a constant, where the constant is e over 2 minus the semicircle law. And we are assuming that the energy is more than 2. Okay, so but the point is that then what we obtain here is E plus an integral of the product of dmx. So it's exactly the same. And the only difference is that now H is computed in this translated matrix. Okay, and now the point is we want to look at this. This is like, we call it remainder term, and it depends on L. And our goal is to show that when L goes to infinity, this term disappears. And the result will just be, so this average converges to the constant. Okay, so the goal, show that the limit L going to infinity of remainder L is equal to 0. Okay, so again, we are in a good position to try to apply a transfer operator. And we can do it. So we have this dual representation again. Dual representation. Oops. Can I go on 5 minutes?
Okay, 5 minutes. Yeah.
Yeah. So just to get at least to the formula, just to, because I'm realizing that I'm already at, it's already 4 as usual. Okay, I will I just, okay, so I'll just give what is the dual representation. And okay, so the dual representation x0, x0, I take away the constant, so we can write again exactly as before, L plus x0, fL, observable, L minus x0, f, right? And now I will just write maybe the transfer operator, which is the only thing that really is important here. So again, it will be an operator with integral kernel, m prime, f of m prime. And now the kernel, m prime, is given by exponential minus v of m times exponential minus w square over 2 super trace m minus m prime square. Okay, so the good news is here we have no I, so no oscillation. The bad news is, well, we still have Grassmann variables. So we have to get rid of them and map to a standard. So we want to map to an ordinary, a standard. So we just show how to map to the standard operator. Okay, so what is the idea here? Here the idea is that we can diagonalize our matrix. So the idea here is diagonalize M. So remember that M is A, I, B, rho bar, rho. Now I know that if you look at this I, it doesn't look like, but actually this matrix is more or less self-adjoint matrix, which means you can diagonalize it with unitary matrices. But now the unitary matrices will be matrices containing Grassmann variables. So actually we can write it in this way. Lambda 1, I, lambda 2, U inverse, where U is the exponential of a matrix, psi and eta, where these are Grassmann variables. So these are super unitary matrix. Okay, and now same game, if our function is invariant under, I call it M prime, under unitary rotations, well then there exists a function little f, which is defined on R2, on two variables, taking complex values, so lambda 1 and lambda 2, such that f of M is little f of lambda 1 and lambda 2. And the operator applied to capital F, computed in M, is just a standard operator computed to the function little f, computed in lambda 1 and lambda 2. Because this function depends only on the eigenvalue of the matrix. Okay, so now the last. So how does this T looks like? Well, of course, we had Grassmann variables. The result can, as in the previous case, it will not be totally trivial. So T looks like this. This is exponential minus V lambda times delta 0 plus an operator R times identity minus delta 0. And this delta 0 comes from the fact that we had the Grassmann variables, and we pay a price when we transform them into an ordinary operator. Okay, but still, R is very nice. R looks like that. This is a, well, also R may be scary. D, lambda inverse, when lambda is a multiplication operator. So we multiply by lambda 1 minus I lambda 2. And the D is just the convolution with the Gaussian. So this is just a W square, I think divided by 2p. Yes, the integral of exponential minus lambda prime square, W square over 2, f of lambda prime, d lambda prime, and integrate in R2. Okay, so again, this seems, even if, okay, it's true that we have no oscillation, but V is complex. And also here, this lambda is complex. So we have a complex operator. This, we cannot avoid this. Another thing that is a bit scary, we have this delta 0. And, well, there is also, in addition to this problem, we have this lambda inverse. Lambda inverse is actually integrable, but it's not clear when we when we apply it as an operator if there is some problem. And actually, the answer is no, because if we take a high power of these, well, all the lambda disappear except the one at the beginning, and the one at the end. And actually, we can even reorganize these in a very nice symmetric way. Plus V/2 times lambda inverse. So actually, eventually there is a problem in one point. But when we take high powers of the operator, the only operator we really need to study is this. And actually, if we take the norm of this, actually the absolute value of this, so real part, the exponential real part, this operator has norm which is smaller than 1 minus some constant divided by W. And W, so this is strictly smaller than 1 because W is much larger than 1. So again, if the function we apply our operator to is 0 in 0, well then t to the L applied to f is just exponential minus v r to the L applied to f. And now the game is that, okay, at this point we can, even if you cannot say directly, well, this will converge to a projection, we can still prove that it does converge to a projection. And then what remains to prove is that the projection you converge to is the projection on a certain eigenvector. And this you have to construct at least an approximation more or less explicitly. But it can be done. So maybe I should stop here. Maybe the last remark is, so to actually now make this construction rigorous, so we want to find, so as in the case of the standard case, we want to find V0, which is the top eigenvector. And more or less, we want to prove that the norm of T1 is smaller than 1. So this corresponds to prove that this norm is smaller than 1. And to find V0, actually, it's better to go back in the previous representation, so in this strange operator with Grassmann variables, because there it's much easier to see how V0 should look like. So the point is that here you have to play a bit with both representations. One representation may be more useful to compute something, and the other more useful to compute certain bounds. So I think maybe I'm already out of time, so I will stop here.
Yes, thank you very much. Are there questions? So perhaps I have one question about the Anderson model. So one difficult question is to prove delocalization.
Yes. Well, actually, in dimension 1, there is a paper, so Klein and someone else. So actually, you can use this method also to prove localization in dimension 1. So in dimension 1, you expect exponential localization. And in dimension 1, they can actually use transfer operator to also to prove localization. The transfer operator is more complicated, of course. But they can still prove a exponential decay of, they take the Green's function square, they prove exponential decay, but it's a bit weaker than the exponential decay you would expect, but then they prove that in dimension 1, this weaker result is enough. So yeah, so it's nice. In dimension 1, you can really do a lot. That's the only example where I know that you can prove something about localization. I think there are more other results. I'm not sure, but I think Christian Seidel, he did more stuff using transfer operator. Maybe he got more results in 1D or quasi 1D. But I should check. Yeah, sorry.
Thank you. Yes, Jan?
Yeah, so you explained very nicely how one can translate some problems into the supersymmetric language. Now, suppose one does not care about supersymmetry, but one wants to have results about the initial problems.
You mean sorry, the classical transfer operator, or you're asking really about classical?
Well, I'm asking about this random.
Yeah. Yes.
So,
So during the random Schrödinger or a random
yes,
band matrix
yes.
also, yes.
What one can show about this this random classical? I mean, these random operators, which one cannot prove without supersymmetry. I mean.
Oh wait, okay, maybe I should. Well, band matrix is a bit more difficult to. Also there you can prove a lot of stuff. But for instance, from the random Schrödinger operator, you can prove a lot of results without any supersymmetry. In a way, it's a kind of rare to use the supersymmetry for random Schrödinger, I would say. So for random Schrödinger, you have other tools. So you have these this fractional moment method, which allows you to prove exponential localization at high disorder in any dimension or at the bound of the spectrum. And it does not use supersymmetry at all. You just work with the resolvent and you play with the resolvent. So you remain at the level of, where am I? Here, above. So you remain at the level you remain at the level of this. Or more precisely, you have to study Z minus H inverse, and then actually what you study is the average of these to the power S, where S is smaller than 1 and larger than 0. And there are very good, nice and powerful tools that allow you to prove a huge amount of results on the random Schrödinger. So you can prove, and in dimension 1, you can prove, I think in dimension 1, you can prove also localization using other tools. You don't need necessarily. For the, okay, I'm not sure if you're asking about that, but so for random Schrödinger, what you know is that in dimension 1, you always have localization and exponential decay of the eigenfunctions. In dimension 2, you expect always localization, but it's proved only for large disorder. And for weak disorder, it's still, I don't think it's still proved. And for dimension larger or equal than 3, well, you have localization at large disorder, and you expect delocalization at weak disorder. And this is, as far as I know, open. This is open. And this is proved. And yeah, so so let's put it like this. So random, there is a huge work, a lot of research on random Schrödinger. And but still, this weak disorder part is still resisting. So looking for other toy models where maybe one can prove something, this was one of the reasons to introduce this random band matrix. And there it turned out that this supersymmetric representation allows you to, maybe not to rigorously prove, but at least to guess a lot of properties. So in physics, it's much used to say, well, we expect this or that. Making this rigorous is pretty hard. So there are only very few cases where you can actually make this rigorous. For band matrix, there are other tools to prove. So in dimension 1 for band matrices, so where am I? For band matrices, it's somewhere down. Okay, for band matrices, if I am in dimension 1, then you know that if the bandwidth is larger than the square root of n, okay, here I should now say, let's say this is a matrix n by n. Okay, if W is larger than square root of n, then you know that in the limit you obtain linear statistics and delocalized eigenvectors. And if W is smaller than square root of n, you have localization. And there are several works that do not use supersymmetry that prove this or almost this. Maybe you get to powers that are not exactly square root of n, but you are very near to that. So I'm not claiming that supersymmetry is the only method.
No, this was not my question. But I mean, I agree that it is a beautiful, beautiful formalism, but
there are other tools. I agree, and sometimes
is there something important that one can prove only with supersymmetry? Or which one can prove? I mean,
for example,
the best way to prove is supersymmetry.
Well, there are, for example, duality relations that are very hard to prove without supersymmetry. For example, let's see. Well, maybe I'll give you an example. Which maybe first. For example, if you look at the density of states, so I look exactly at this problem, but now I am in dimension 3, or actually 2 or 3, so larger than 1. Okay, and now I'm asking, I want to study the function f of E, which is, so I want to take this limit, I take the imaginary part, so let me take this away, and I want to take the imaginary part of this, and I want to study this as a function of E. And I take actually, I can even take, before I take the limit, I can even take here epsilon going to 0. So this is really only a function of the energy. So this is the limit in infinite volume of the density of states. Well, you can study this function in a pretty detailed way. You can show this function is differentiable as many times as you want, and it looks like the semicircle law and so on. You can get a lot of information, and actually the only way I know how to prove it is using supersymmetry. I don't know any other way to do this. There are also sometimes supersymmetry gives you a nice relation which is not at all obvious to see directly. So for example, okay, here I have to go down. Now this is, now I will take another model that I hope it's not so I take another model where hope this is again this is a model motivated by quantum diffusion, but it actually has applications as a random walk in a random environment. And now the point is you have a random walk in a random environment, you have a mixing measure, and this measure looks pretty complicated. This measure is something like that. I have a measure which is of the form, I have a sum of nearest neighbor point, cosh of ti minus tj, where these are real variables, something like that. There is some cosh, I don't know, t0 minus 1. There is here a determinant of a matrix that depends on t, square root, product over j dtj. Now, this looks like a horrible measure, but it is the mixing measure of a history-dependent stochastic process. And this measure has a huge number of symmetries, but that they are very, very hard to see if you do not go through the supersymmetric representation. Actually, you have, I can put here a certain function f of t, and then also, okay, first, and this integral is equal to 1. And it doesn't matter what I put here as coefficients. And it's not at all easy to show directly that this integral is equal to 1. Unless you prove that, okay, this is the mixing measure, but if I just give you this integral, it's very hard. But the point is, I can rewrite these, I can represent these as something like it's a spin model with real and Grassmann variables. And then I see automatically by the symmetry that this has to be 1. And in the opposite, I can start from the supersymmetric model. I take some function, I use the symmetry. I know that the integral has a certain value. Now I go back to my starting integral, and if I hear some complicated function of t, and I still know that the integral of this very complicated function of t is 1. And I remember we were working on this model and we were trying to prove results, and we needed this kind of identities, but to prove them directly, we couldn't find a way. Except when you already know what is the identity, and in some cases you take some limits, you already know what you have to find, then you can prove it, maybe with some limits or so. But there's no way you can guess it. Okay. So in that case, yes, it does. It really gives you something that you cannot prove, at least as far as I know, in another way.
Thank you. Are there further questions?